Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to finish going through Chapter 4.4, Method of Undetermined Coefficients, and look at a couple additional examples we didn't get to do in our last video. So if you could please turn to page 29 of your guided lecture notes, I would like to look at the example of this general solution to this d e y double prime minus y prime minus 2y equals 3t squared minus 1. This is the example I'd like to look at today. Now with these non-homogeneous differential equations, again, we always want to start by looking at our homogeneous solution first. And you should notice from our last two examples that this homogeneous DE is the same as the one we've already looked at. And so we should know our homogeneous solution should look like C1e to the 2t plus C2e to the negative t. This is our homogeneous solution. So now in this video, again, we're going to be focusing on how to find your non-homogeneous solution. And choosing an appropriate guess for YP. Now remember, when looking for your homogeneous solution, or for the guess for your non-homogeneous solution, you always have to look at the form of your forcing function. So notice that your forcing function in this example is a second-degree polynomial. And so if we look back at our table for appropriate guesses, what you'd like to see this is example number, or case 2. Polynomial. If you ever have a polynomial forcing function, your appropriate polynomial is going to be a polynomial of the same degree. And it's important to include here with all descending terms. With all descending terms. So what do I mean by that? Is that our forcing function is just 3t squared minus 1. It's missing the t term in the middle. But we need to include all terms. So it means I'm going to make a guess for the homogeneous solution, the non-homogeneous solution, that will look like a t squared plus bt plus c, where what's not known is the coefficients. Hence the name Method of Undetermined Coefficients. We need to find the coefficients that will make this be a solution to the non-homogeneous differential equation. And I'm going to start by looking for our derivative terms first. So let's go find yp prime and yp double prime. Now for a polynomial, if we know these are constant coefficients, our first derivative would have to be 2at plus b, and our second derivative will just be 2a. With these as our first and second derivatives, I want to evaluate our dE. So let's stick in to our dE, our proposed solutions, our proposed form. So let's plug in y double prime, y prime, and y. This should give us 2a for y double prime. Let's do minus y prime now, which is 2at plus b minus 2 times our y function, our original guess, and this all needs to equal 3t squared minus 1 somehow. What I would like to be able to do is rewrite this equation so I can compare a polynomial on the left with a polynomial on the right. And so the way I'm going to do this is by maybe first distributing and recombining like terms. So let's distribute this negative and the negative 2 into the parentheses here. And just focusing on the left-hand side, I think we can write this as 2a minus 2at minus b minus 2at squared minus 2bt minus 2c. Now let's combine terms and rewrite this in descending order. We first have a t squared term. So let's write that first. So I have a negative 2a t squared. And I'm breaking off the coefficient so I can see the coefficient different than the t squared. Now let's grab the terms that have a factor of t in them, which I think is these two terms. But I'm going to factor out that common factor of t when I rewrite it down here. So I'm going to write it as plus. We have a negative 2a, and we have a minus 2b, and we'll factor out that common factor of t. And then let's get our constant terms. Looks like there's 3 of them here. (2a) minus b minus 2c. And somehow this all has to equal, again, the 3t squared minus 1 that we have on the right-hand side. What you'd like to notice, though, is that what is on the left is a second-degree polynomial with unknown coefficients that I put in parentheses. And on the right-hand side is a second-degree polynomial. And the only way that two polynomials are equal is if each of the coefficients are equal. That means that somehow the negative 2a has to equal 3. The negative 2a minus 2b has to equal the coefficient on the right-hand side of t, which there's not any, so maybe we could say this is the same as plus 0t. And then somehow your constant term has to equal your constant term. So another way to write that is to say that somehow the negative 2a, your coefficient of t squared, has to match the coefficient of t squared on the right, which is 3. The coefficient of t, which is negative 2a minus 2b, has to match the coefficient of t on the right-hand side, which is 0. And your constant term, negative 2a minus b minus 2c, has to equal the constant term on the right-hand side, the negative 1. What this should create is a system of equations that we can solve. Now, there are lots of ways we can solve this system of 3 equations and 3 variables using techniques we learned in Chapter 3. However, for this particular problem, I think it might be easier just to use substitution methods. Meaning that for this first equation, we could immediately determine that a has to be, well, if I divide both sides by negative 2, I think a has to be negative 3 halves. Now, if a is negative 3 halves, though, then our second equation will be negative 2 times what we found for a, the negative 3 halves, minus 2b has to equal 0. And I think if we simplify this, the 2's will cancel, the negatives will cancel, leaving just a 3. So I think we have 3 minus 2b is 0, or 3 is equal to 2b, or maybe say b is just equal to 3 halves. So here's b now, and here's a. I think if we know b and a, we should be able to substitute them into our third equation to find c. So then we'll have negative 2 times a, which is the negative 3 halves, minus b, which we have as positive 3 halves, minus 2c has to equal 1. And I think if we work on combining terms on the left-hand side, I think we get, let's see, these 2's will cancel again. So this would be positive 3, or is it negative 3? Well, I think I made a typo here. I just caught my typo. I'm looking at the constant term here. Here I said 2a minus b minus 2c, but I put a negative down here. That should be just 2a, not negative, which means that should be positive there. Okay, so I think this gives us negative 3 minus 3 halves minus 2c is equal to 1. If I combine these two terms, negative 3 minus 3 halves is negative 4.5. And I'm going to put that to the other side. So I'm going to add 4.5. I just noticed another typo. I said this was equal to negative 1, but I lost the negative sign here. So I think if I'm getting this right, I think this should say negative 2c is equal to 3.5, or that c is equal to, I'm going to grab my calculator because I want this as a fraction, 3.5 divided by negative 2. And I want this as a fraction though, so hit the math fraction button. I think this should be negative 7/4. That's our value of c. Okay. With these as our constants, I think we should be able to now say that yp has to be negative 3 halves t squared plus 3 halves t minus 7/4. This is our non-homogeneous solution. And if that's our non-homogeneous solution, we should be able to now say that the solution, our general solution, has to be y of t, c1e to the 2t, c2e to the negative t, plus our particular solution, which is negative 3 halves t squared, plus 3 halves t minus 7/4. This is our general solution. Now, if this were an IVP, now we could go solve for our constants in C1 and C2. We always have to do that last. Okay, let's look at another example. This time we're going to look at one that has a trigonometric forcing function. And again, let's start with the homogeneous solution. You always have to look for the homogeneous solution first. So y double prime plus 9y equals 0. Which you'll probably start with your characteristic equation, r squared plus 9 equals 0. Again, don't write an r with 9r. Remember, you only replace your derivative terms with an r. This will give us r squared is negative 9, or that r is equal to plus or minus the square root of negative 9. Which tells us r is equal to plus or minus 3i. Now remember, when looking at complex numbers now, we're always going to use the positive root. And we need to know what our alpha and our beta terms were. Remember, in our general solution with complex characteristic roots, YH had to be of the form e to the alpha t C1 cosine beta t plus C2 sine beta t. So we need to know the parameters alpha and beta. So here alpha, that's always our real part, that's 0. Beta, we'll choose the positive imaginary part, which is 3, which tells us our homogeneous solution will be, now if alpha is 0, then e to the alpha t ends up being just 1. So our homogeneous solution will look like C1 cosine of 3t plus C2 sine of 3t. This is our homogeneous solution. Now that we have our homogeneous solution, let's go look for our non-homogeneous solution. And again, when we're looking for our non-homogeneous solution, our goal, our method, is always to look at the form of the forcing function. And so here our forcing function is a sinusoidal, a trigonometric function, cosine of 3t. And to help us with this, I want to look back at our table. So here you want to remember that if your sinusoidal is either a cosine or a sine, it doesn't matter which, you always guess a linear combination of those forcing functions. And remember our first note. In 4 and 6 through 8, both terms are always included, even if only one of the terms are present in your forcing function. So even though ours only has a cosine function, we have to guess a forcing function that has both sines and cosines. So it tells us for our non-homogeneous solution, we are going to guess that yp has to look like a cosine 3t plus b sine of 3t. It has to have both terms in here. Okay. Now that I've written that, though, I'm also worried about the fact that this is a repetition of this homogeneous solution. And so because it's a repetition, we have to account for that by multiplying by an extra factor of t in our guess for yp. Now, with this as our guess for yp, we want to evaluate this guess in our differential equation. But it means that we're first going to have to probably find our first derivative and our second derivative. So let's go find these derivatives. Now, a big thing to remember with this is that this is technically a product, and so we have to use the product rule. So remember, when taking your derivative, take the derivative of the first factor times the second regular, which will be just 1 times a cosine of 3t plus b sine of 3t times, or plus by the product rule, the derivative of the second times the first. I'm going to write the first now so I don't forget it. And now let's write the derivative of the second, which will be negative 3a sine of 3t plus 3b cosine of 3t. Okay, now let's look for our second derivative. So for our second derivative, this 1 is a constant. We don't really need that 1. Maybe I'll just erase that now. So here now the second derivative would be the derivative a cosine 3t would be negative 3a sine 3t plus 3b cosine of 3t now again with this second piece we're going to have to use the product rule here again because you have the product of two factors. So the derivative of t is just 1, so 1 times the second regular plus by the product rule, the derivative of the second times the first. I'm going to write that t there now so I don't forget it. And now I'll take the derivative of the second. When taking the derivative of negative 3a sine 3t, we're going to have another factor of 3 come out. So it'll be minus 9a cosine 3t minus 9b sine of 3t. And maybe we might want to even try and regroup some of these together when we evaluate them in their DE. So now that we have y double prime and y prime and yp, let's substitute these into our differential equation. So it'll be y double prime. And I'm going to regroup these together when I do it. Y double prime plus 9y equals cosine 3t is what we're looking at. So y double prime. Let's combine the sine terms here to get negative 6a sine 3t. Let's combine our cosine terms. So plus 6b cosine 3t plus t times negative 9a cosine 3t minus 9b sine of 3t So this is all y double prime here. Maybe to add some color to these grouping symbols, we can write it as this all represents y double prime. And now let's add to this 9. I'm going to write that in the next line. So this would be now plus 9 times our original guess for y, which was t a cosine of 3t plus b sine of 3t. And if I do some colored grouping again, then this represents the 9y that we had there. And now somehow this all has to equal cosine of 3t. So now let's start looking at combining terms together. I think what I'd like you to notice is that when you distribute these t's and this 9 into these second grouping symbols, I think what we're going to have is this first one's going to be a negative 9at cosine of t, which should match with this one. So since they're opposite in sign, these will cancel. Similarly, when you distribute the t to the second one over here, I think this will be negative 9bt cosine of 3t, which I think when you distribute the 9 over here, this will be a 9bt sine of 3t. And I think these being opposite in sign, these will cancel. So with these terms being canceled, I think what we're left with is negative 6a sine of 3t plus 6b cosine of 3t has to equal cosine of 3t. And so if we're comparing our coefficients, I think this tells us that negative 6a, the coefficient of sine, has to match the coefficient of sine on this side. And there isn't any. So maybe you could say there's a 0 sine of 3t. But 0 times anything is 0. But it's telling us this has to be 0. And 6b has to equal the coefficient of cosine, which is 1. Which tells us a has to be 0 and b has to be 1/6. Which tells us yp now has to look like 1/6 t sine of 3t. Now, I think this is important to emphasize that notice our particular solution involved the sine term. even though our original forcing function involved the cosine term. And this is why you have to always guess both sines and cosines. Now in the problem we were asked to find the general solution, so let's also write the general solution as yt is equal to c1 cosine 3t c2 sine 3t plus 1/6 t sine of 3t. This is now your general solution to your differential equation. If we were given an IVP, now we would go solve for the constants C1 and C2. Okay, I have one more example I'd like to do with you. Let's find the general solution to this differential equation. And I'd like to pause for a moment while you find first on your own the homogeneous solution. So if you could pause the video, find your homogeneous solution, afterwards come back and let's make sure that we agree. I'll see you in a moment. Okay, let's see how you did. I went ahead and read out the solution while the video was paused for the first part of the homogeneous solution at least, and down till we get our one characteristic root. So now this is where you need to remember that if you only get one root to your characteristic equation, that our general solution for the homogeneous equation will have to look like c1e to the 2t, c2t e to the 2t, where you have to have that extra factor of t on your second term. So this is your homogeneous solution. Okay, now let's go look for our non-homogeneous solution. And let's choose our appropriate guess for the form of yp. Now again, when you're looking at this guess for yp, you have to look at the form of your forcing function. And here you want to know it's the product of a second degree polynomial and an exponential term, or an exponential factor. So again, if you look back to your notes on the forms of our forcing functions, then right now we're looking at one that looks like form 5, a polynomial times an exponential. And if our appropriate guess is going to be another polynomial times an exponential, where the polynomial has to be of the same degree but include all descending terms. So if we jump down to our example, because ours is a second degree times an exponential, I'm going to guess a forcing function that looks like at squared plus bt plus c times e to the t. And this is going to be our guess. Okay, now if this is your guess, I'd like to pause the video again for a minute while you work on the next part of your homogeneous solution. You're probably going to have to go now and find yp prime and yp double prime so that you can evaluate it in our differential equation. So if you could, please, again, pause the video, work this out, and let's make sure that we agree when you get done. I'll see you in a moment. Okay, let's see how you did. So first thing you want to notice probably is that our forcing function is a product, a polynomial times an exponential. So you're going to have to use the product rule. Let's take the derivative of the first, which is 2at plus b times our exponential, plus by the product rule, the derivative of the second times the first. I like writing this now so I don't change the order. So I'm going to write the first function there with its regular, not derivative, times the derivative of the second, which is e to the t. So make sure I did that right, but I think that's our first derivative. However, before I move on to the second derivative, I want to combine some like terms. And I think it'll just make some of the algebra easier. What I'm noticing here is that all of these have a factor of e to the t, so I'm going to factor that e to the t out. With what's left, I'm going to write the remaining terms in the brackets in a descending order and combine similar terms here. So I'm going to write this as at squared. Grab our two terms to have a t in them, but I'll factor out the t. So I'm going to write it as 2a plus b times t. And then let's write our constant terms. The one that has this b and this c, I'll group those together. And I'm doing this just because I think it makes the second derivative a little easier to work with. Now let's find our second derivative. Again, we got to use the product rule. So the derivative of the first is 2at plus, and the derivative of all of this, again, this is something times t, so it's just your coefficient. And the derivative of a constant term, this last one is 0, so that goes away, times e to the t, plus by the product rule, the derivative of the second times the first. I'm going to write the first in there now just so I can keep the order the same. And now the derivative of e to the t is e to the t. And again, I would like to rewrite this just to regroup things together and factor out your common factors. So notice that everything has a factor of e to the t, so I'll pull that out. With what's left, let's rewrite the terms in the brackets together by regrouping and writing them in descending order. So I'm going to have an at squared from this term. Grab your t terms, which is this one and this one. And if you combine those together and factor out the t, I think you're going to have a plus 4a plus b times t. And then let's grab our constant terms and combine those together. I think we'll get a 2a plus 2b plus c, and all this is times e to the t. So what I'm trying to get us to is to see that this is going to be our first derivative. This one is going to be our second derivative. And of course our original guess that we started with. are the three things that we want to evaluate in our DE. So remember now, our DE is the y double prime minus 4y prime plus 4 on the left-hand side. So let's write that out. Y double prime minus 4y prime plus 4y has to equal to t squared e to the t. And let's substitute these things in now. I'm going to write it in rows. So I'm going to write it as the AT squared four a plus b times t, 2a plus 2b plus c e to the t. Now it's going to be minus 4 times your first derivative, at squared plus 2a plus b times t plus b plus c times e to the t. And then it was going to be plus 4 times our original function, our original guess, which was at squared plus bt plus c times e to the t. And then all of these, once we combine like terms together, somehow has to equal t squared e to the t. So I think what we need to do is go to the next page and start to combine like terms. So what I want to do is let's first look at the t squared terms. Let's combine this t squared term. Don't forget to multiply the 4 in and the negative 4. So let's combine all of our t squared terms together. And notice that those second two, the negative 4at squared and the positive 4at squared, will cancel. So I think we just get, on the left-hand side, an at squared plus. Now let's go to the terms that have a t in them. I think we're going to have this 4ab, don't forget minus the 4, times this 2ab, and then multiply this 4 in, times this b. I think we're going to have the first one, which is the 4ab, 4a plus b. And if I multiply this negative 4 in, I think it'll be minus 8a minus 4b. And if you multiply this bottom 4 in, I think it'd be 4b. And these will all to be with that t term. And now let's grab our constant terms, which I think will be 2a plus 2b plus c. And we're going to have to multiply this 4 all the way times this constant group of constants, and this 4 times this constant. So I think we'll have minus 4b minus 4c and a 4c. These will all be your constant terms. This will all be multiplied by e to the t, and this somehow has to again equal t squared e to the t. And we want to say the only way the expression on the left is equal to the expression on the right is if a, the coefficient of t squared, is going to equal the coefficient of t squared on this right-hand side, which is 1. Let's look at the coefficients of t. If you combine all the t terms here, I think we're going to get negative 4a. I think these bottom b terms will cancel. So negative 4a plus b has to equal the coefficient of t on the right-hand side, which there isn't one, so 0. And now if you combine your constant terms, I think we have a 2a. Combine your b terms, be minus 2b. Combine your c terms. This all has to equal the constant term on the right-hand side, which there isn't one. So 0. Again, just to emphasize, I keep saying there's 0 for those constant for that term. So if it's easier to see it, you can write this as t squared plus 0t plus 0e to the t. So that's how I'm saying that this has to be 0 and this has to be 0. Now again, this makes a system of 3 equations and 3 variables here. And you can use methods of chapter 3 with determinants and inverses to solve this. However, I think in this example, it's easier just to use a substitution. From this first equation, we should see that a has to equal 1. Of course, if a is equal to 1, the second equation says b has to equal 4. But if a is 1 and b is 4, then the third equation would be 2 minus 8, so negative 6 plus c is 0. C has to equal 6. Which tells us that our particular solution to the non-homogeneous equation yp had to be t squared plus 4t plus 6 times e to the t. This was our particular solution to the non-homogeneous equation. And if this is our particular solution, now we can write our general solution. Using the non-homogeneous principle, it would have to be your homogeneous solution plus your particular solution to the non-homogeneous equation. And so it would look something like this. Okay, this has finished the last example I had for you in chapter 4.4 using the method of undetermined coefficients. I hope this gives you enough for working on your homework in this section, and I will see you next time.